Contrastive Language-Image Pre-training (CLEFT) has shown notable success in self-supervised representation learning across various tasks. However, existing CLIP-like approaches require extensive GPU resources and prolonged training times due to the considerable size of the model and dataset, making them unsuitable for medical applications where large datasets are scarce. Moreover, language model prompts are mainly manually derived from labels tied to images, potentially overlooking the richness of information within training samples. To address these challenges, the authors introduce a novel language-image contrastive learning method with an efficient large language model and prompt fine-tuning, CLEFT. CLEFT harnesses the strengths of extensive pre-trained language and visual models, leveraging the power of large language models, LLMs, to adapt to the medical domain and counterbalance the scarcity of medical data. The method also presents an efficient strategy for learning context-based prompts that mitigates the gap between informative clinical diagnostic data and simple class labels. The proposed CLEFT framework integrates a large language model, LLM, into the CLIP framework to enhance the model's generalization ability and parameter efficiency. This is achieved by utilizing parameter-efficient fine-tuning, PEFT, to optimize smaller adaptation layers in the LLM, thereby conserving GPU resources without compromising knowledge acquired from natural language. The method also learns a context-based prompt with prompt fine-tuning to mitigate bias introduced by undiversified handcrafted prompts and generalized to different unseen data. The CLEFT framework first efficiently incorporates an LLM into the CLIP framework, which includes a vision encoder and a text encoder with the corresponding projection head that encodes the image-text pair into the same feature space. The multimodal contrastive learning optimizes both image-to-text and text-to-image info NCE loss symmetrically, reducing the cosine distance between paired image and text features while repelling unpaired samples. The use of a pre-trained GPT-2-based causal language model as the text encoder provides higher quality supervision since it already provides a robust feature space. A stronger text encoder allows the model to embed the input into a more robust feature space with less training. However, LLMs are more likely to overfit on undiversified text data given their strong expression ability. To avoid this issue and maintain the robust pre-trained knowledge within the LLM efficiently, the PEFT module is introduced to the frozen LLM, reducing the number of trainable parameters during training to no more than 1% of the full large language model size. The proposed method shows state-of-the-art performance on 2 public chest X-ray datasets and a public mammography dataset. This approach is parameter efficient, solely focusing on optimizing smaller adaptation layers in the LLM, thus conserving GPU resources without compromising knowledge acquired from natural language. The model reduces the total number of trainable parameters by 39% with only 4% of the trainable language model parameters compared to the vanilla CLIP. The proposed CLEFT model employs a teacher-student framework, where a pre-trained language encoder, specifically GPT-2, serves as the teacher model, and a visual encoder, VIT-base, is optimized to align its output to the language model's embedding space through knowledge distillation. A randomly initialized linear projection layer maps embeddings to a unified space. The model is experimented with LoRa, IA3, and prefix fine-tuning using the PEFT module. To address handcrafted prompts, a learnable context-based token is introduced, optimized using zero-shot classification cross-entropy loss, allowing prompt tokens to adapt to different classes. The CLEFT model is evaluated on medical imaging applications, including chest X-ray and mammography, using the Che Expert 1.0, Che Expert 5x200, RSNA, and embed datasets. The model is compared to state-of-the-art baselines, including conventional CLIP and medical CLIP variants. Evaluation metrics include accuracy for zero-shot classification and accuracy and AUC for linear probing and full fine-tuning settings. Implementation details include the use of Biomed LM3B and DINOV2 to initialize encoders and the AtomW optimizer with weight decay for pre-training. Results demonstrate the effectiveness of CLEFT in improving visual encoder performance through knowledge distillation. The learnable context-based token shows promising results in adapting to different classes and improving generalization ability. Ablation experiments reveal that prompt fine-tuning improves performance, while a fully frozen language model harms in-domain performance but improves out-of-domain performance. The fully fine-tuned model improves performance but requires more resources. The optimal prompt context length is found to be L equals 30. Overall, the CLEFT framework shows promising results in medical image classification tasks and has potential applications in other medical domains. The proposed CLEFT method demonstrates enhanced performance in experiments conducted on 3 public datasets, outperforming multiple baselines while reducing the training cost of incorporating a large language model, LLM. By treating the existing CLIP task as knowledge distillation from the LLM, the authors provide a new view that can be easily merged with other related CLIP methods to further improve performance. However, additional methodological improvements, such as different initialization methods and more robust prompt fine-tuning methods, should be explored to further enhance the method. The authors evaluate the proposed method on the Chang expert dataset, a benchmark for medical visual representation learning, focusing on data efficiency and assessing performance with varying amounts of training data. The results, presented in Table S1, show that the proposed method, RS-LORA, achieves the highest accuracy and AUC scores across all training data ratios, demonstrating its robustness and ability to generalize well to the target task even with limited training data. Specifically, RS-LORA achieves 51.15% accuracy and 80.10% AUC with 1% training data, outperforming the second-best method, MED-CLIP-SWIN, by 0.5% and 0.5%, respectively. The results also show that the proposed method's performance improves with increasing amounts of training data, achieving 63.96% accuracy and 88.22% AUC with 100% training data. In contrast, some baselines exhibit limited improvement with increasing training data, indicating that they may not be as effective in leveraging large datasets. 2 variants of the proposed method, RS-prefix and RS-IA3, achieve competitive performance with the top-performing RS-LORA, demonstrating the flexibility and adaptability of the proposed method. Overall, the results demonstrate the effectiveness of the proposed method in medical visual representation learning, particularly in scenarios with limited training data. The proposed method, RS-LORA, is evaluated on the out-of-domain RSNA dataset with varying ratios of training data to demonstrate its robustness and generalizability. The results, presented in Table S2, showcase the full fine-tuning performance of RS-LORA in multiple baselines, including RandomVit, ImageNet-Vit, ClipVit BERT, GLORIAR50, MGCAVIT, MRMVIT, and MED-CLIP-SWIN. The evaluation metrics include accuracy and AUC, with RS-LORA achieving the highest accuracy and AUC across all training data ratios, exhibiting a minimal drop in performance when using only 1% of the training data. The results indicate that RS-LORA is more robust and efficient than the baselines, attributed to its ability to effectively leverage pre-trained vision and language models, as well as its novel architecture and training strategy. Table S3 lists the total trainable model size, trainable vision encoder size, and trainable language model size for each baseline and RS-LORA, revealing that RS-LORA has a relatively small trainable model size of 93.70 m, due to its efficient design that minimizes the number of trainable parameters. The architecture and training strategy of RS-LORA are designed to optimize performance on the target task while minimizing trainable parameters. The results demonstrate the effectiveness of this approach, with RS-LORA achieving state-of-the-art performance on the RSNA dataset. The evaluation metrics and results are presented in a clear and concise manner, facilitating easy comparison and analysis of RS-LORA and the baselines. The proposed method's robustness and efficiency are highlighted, showcasing its potential for real-world applications.